So welcome to MathStat 341. This is, I don't know, probably around lecture 24. And what I want to do is I want to spend the last few classes we have talking about applications of what you've seen and what classes you might take next and what would you get out of them. And so the goal today is to review what we've been doing over the semester with a focus on applications. So this is a talk I've given numerous times. I've worked a lot on this with students at Williams and at other places. So out of curiosity, how many of you have heard of the German tank problem? Okay, good. Not too many people have heard of it, so that's great. I'm sorry? It was in the textbook. Sometimes it's better not to mention that out loud. I'll be careful what I'm going to say when I'm going. So this is a great example, and you can actually watch the video of just how the German armies advanced in World War II. One of the reasons for their success was their excellent use of tanks. And it was extremely important for the Allies to know how many tanks were the Germans producing and where were the tanks being deployed. So how do you figure this out? Well, one possibility is you could just go to a German tank factory and show your credentials. You know, you're a reporter from the London Times, and you're here to interview them about production. Not going to happen. So how would you try to figure out how many tanks there are? What would you do? Sending reporters is not going to work. What could you do? So that's one thing. So one thing is to use statistics and mathematics. How could you do it if you don't use statistics and mathematics? What could you do instead? How could you get data? What could you do?
Are you ruling out spy planes?
No, I'm not ruling out. So suggest those. So you take videos, you send surveillance flights overhead, try to get a sense of what the production is. Send spies, try to get a look at the paper. Look at material being sent to the production plants and try to estimate how many tanks are being produced based on what's going in. So there's lots of ways to gather data. Which do you think works better, the spies or the mathematicians, statisticians? Yeah, why? There's that, but also I'm giving the lecture, right? And so given that I'm talking about this in a stats class, probably the statisticians are doing better than the spies. Okay, so we'll see exactly how much better they do. So just a little bit on my experience, my ability to talk about problems like this. I was an undergraduate at Morse College, and we had a very famous statue of a tank on top of a lipstick in our courtyard. And so I have spent years looking at tanks. All right, so here is the original formulation of the German tank problem. After a battle, you see the serial numbers S1, S2, SK on captured or destroyed tanks. So you see K serial numbers. How many tanks were produced? So given this data, we want to try to estimate how many tanks were produced. Okay, so we will assume the tanks are numbered from 1 to n. And later, and in fact, this was a new result that I did with some students at Williams, we looked at what would happen if instead of starting at 1, you started at some arbitrary number, n1, and went up to n2. And the mathematics becomes a little bit more involved, but similar ideas still work to get the estimate then. A lot of times in statistics, we put a hat to indicate the best estimate in some sense of the quantity we care about. And so we're trying to estimate the number of tanks produced as a function of the maximum observed serial number, that's little m, and the number of tanks that we observe, k. Okay, everybody understand the problem? So there are dangers of both underestimating and overestimating. Can somebody give me a danger of either one? So if you underestimate, you might go into battle and you might not put in enough forces. Excellent. Give me a danger of overestimating. So one thing is you might actually not go into battle. Yes, there's also another danger of overestimating. Misspend resources, you misallocate. You put too many resources into that one battle. There's a lot of great quotes. I love the one from Lincoln in the Civil War. If General McClellan isn't going to use his army, I'd like to borrow it for a time. McClellan was terrific at training his troops. He wasn't so good about actually getting them into battle. And so it is possible to have paralysis by analysis. And so just numerous times the North would not advance on the South. McClellan did not feel like he had enough troops. I always need more troops. And again, in an ideal world, it would be great to have more resources, but there's a cost. Sometimes it's you delay battle. Sometimes it's you put too many resources in one place and other parts of the war front do not get the resources they need. Okay, so what I want to do today is I want to talk about the mathematical preliminaries, which this deep into the semester we should have seen. I'll talk a little bit about the new version, but I'm going to mostly talk about the original formulation of the problem where you start at 1. It's not that bad to start at an arbitrary place. And then a few summers ago, I extended it further with some students as to what if you have several factories where each one of them produces tanks in a range, and you gather data like that. And so now you have to figure out which tank came from which factory. Can you handle something like that? And if the factory this is being recorded, so I'm not going to say too much about what we can and cannot do. And then I'll talk a little bit about how can we use some of the advanced techniques we've done, such as regression, to try to figure out what the formula is. There's a beautiful formula to estimate the number of tanks as a function of M and K. You can get it by pure theory, but you can also get it by doing data analysis. And in the 21st century, you want to learn how to train your computer to do this analysis for you. Okay? Is it a reasonable assumption to have the tanks ordered sequentially? Why? So what's the advantage of having the tanks ordered sequentially? Why would the Germans do that? And don't say Germans being Germans. So you have to keep record. So you might want to know, when is a tank due for various types of maintenance? And if you have things labeled sequentially, if you have some kind of code, this tells you the year, this tells you the month, this tells you the day, this tells you which number it was, you can then very quickly look at the serial number and have some idea of when things should be done. Nowadays, you could, of course, have your strange codes. I just had to update my car rental reservation because 2 more people well past the deadline have said, we'd also like a ride from the airport. So now I got to get a larger car, I got to change the reservation. And I'm looking at I have no idea what this reservation number means, but there's a simple program that they can run it into and then it will spit out something reasonable. We don't have to have something that you can just glance down at anymore. Computers can do all of this. But back in the 1940s, it was very nice to be able to quickly look at a serial number and see when was the tank made, when do you think it's likely to need certain types of repairs or maintenance. All right, so the mathematical preliminaries, which again, by now we should have all seen, we should know what the factorial is. It's the number of ways of ordering n objects when order matters. We define 0 factorial to be 1. N choose k is the number of ways to choose k items from n when order does not matter. So think being a representative as opposed to being an officer, where the officers are different. And then the binomial theorem, x plus y to the n, is the sum of just n choose k, x to the k, y to the n minus k. One of the first times you might have seen this is if they were rigorously proving how do you take the derivative of x to the n. If you want to calculate x plus h to the n, you'd use it with the binomial theorem. Okay, we now need some combinatorial identities. So the first one we need is Pascal's identity, that if you look at Pascal's triangle, n plus 1 choose k is n choose k plus n choose k minus 1. So basically each element is the sum of the elements above to the left and above to the right with 1s on the outside. If you want, you could extend it to having then 0s everywhere else so that the relationship would still hold. We've seen proofs of this, and I'll probably give a quick proof again, just to reemphasize proof by story. And yeah, so here it is. So we have n Red Sox fans and 1 Yankee fan. And we want to know how many ways can we choose a group of k. So we did this earlier in the semester, but it's good to reemphasize this. One of the most powerful techniques we have in combinatorics is telling a story. Take something you want, calculate it 2 different ways. So how many ways can we choose a group of k people from n plus 1? It's just n plus 1 choose k. And then we break it into 2 cases. We're either in the great case when we don't have the Yankee fan with us. So there's 1 choose 0 way of not choosing the Yankee fan, and now we have to choose k Red Sox fans. Or unfortunately, we got the Yankee fan 1 choose 1, and now we have to choose k minus 1 people from the Red Sox. And so this is a proof by story. You could prove this by algebra. Just put in the definition, multiply through, cancel the denominators, do some algebraic simplifications. It's very straightforward to prove. But the proof by story gives you a sense of what's going on and why it's true. It also makes a lot of sense. If you start looking at what's going on, you can see that all the tops add up to n plus 1 and all the bottoms add up to k. Now, you don't combine binomial coefficients by adding the tops and adding the bottoms. But if you're thinking about what's going on, I have to somehow deal with n plus 1 objects and choosing k objects. It makes sense that the tops are something like this and the bottoms are something like that. I can't remember, did I play the Pascal's Mod 2 video for you guys? Okay, so I'm not going to bother playing that, but just a lot of fun stuff you can do in terms of, there's a lot of structure to Pascal's triangle. Okay, so how would we prove Pascal's formula? We proved that. Here is another needed identity. So this is often called the hockey stick identity. The sum of m choose k, where m goes from k to capital N, is n plus 1 choose k plus 1. So what does this mean? Well, if I do the second diagonal, 1 plus 2 plus 3 plus 4, that adds up to 10, which is the number below and to the right. If I do 1 plus 3 plus 6 plus 10, that adds up to 20, which is 1 below to the right. So this is often called the hockey stick identity. Hopefully you can see the hockey stick like that. Why is this true? Well, this is basically your classic proof by induction. And again, when you're trying to prove something by induction, it's really nice if you know what you're trying to prove. And so the base case, if I take n equals k, then both sides are just 1 because there's only one term in the sum. So it's pretty straightforward. And so now what we have to do is we have to do the inductive step. So we assume it's true up to k, up to n. And then, well, if we want to sum from k to n plus 1, we have the sum up to n, and then we have one more term. By induction, the sum up to n is just n plus 1 choose k plus 1. The last term is n plus 1 choose k, and now it just follows by Pascal's identity. So for those of you who are math majors, abstract algebra and real analysis might be in your future where you're going to have to start proving things. And so the more experience you have proving things, the easier it's going to be. Whichever class you take first, I think is going to be the more challenging one. And you want to get a sense of how should I attack problems? How should I try to prove something? For induction, it's always, I assume it's true up to n. Let me find a way to see that in the expression for n plus 1. Because that's how I can then use it. So how can I see the statement for n? Well, let's see. Instead of taking all the terms up to n plus 1, let's take the terms up to n and then add the remaining. That's a standard method in proving stuff like this. All right, so now we can turn to the original German tank problem. And so what I want you to do now is I want you to conjecture. So I have deliberately not told you what the formula is. So I'm just going to ask a really weak question. I want you to be qualitative here. How should our best estimate for the number of tanks depend on m, the maximum serial number we observe, and k, the number of tanks observed? So for example, if I keep k fixed and I increase m, what should happen to n? What should happen to n hat? It should go up, right? The larger value I get for m, the bigger my estimate for n hat should be. What if I keep m fixed and increase k? What should happen? So what should happen to n hat? So I have the same m, think of m as 100, but instead of having 5 tank serial numbers, I have 20 serial tank numbers. It should go, say it out loud. It should go down. Does everybody agree that as m increases, it should go up? As k increases, it should go down? Can somebody give me a formula involving m and k that goes up as m goes up and goes down as k goes down? M over k. Does everyone agree that that's the simplest thing you can guess? Now, can somebody give me a lower bound for n hat? There's 2 lower bounds. N, right? If m is the largest serial number you observe, and the tanks are labeled from 1 to capital N, clearly you have to have n hat is at least m. It's also got to be at least k because you've observed k tanks. But since we're numbering from 1 to n, m is always going to be at least as large as k. So we know it has to be at least m. We know it should be increasing with m and decreasing with k. So the simplest thing I can think of is some function of m and k added to m. And the simplest function I can guess is maybe some constant times m over k. It turns out the answer is m times 1 plus 1 over k minus 1. We'll prove that shortly. Whenever you see an expression in mathematics, you should always ask, is this reasonable? You should try to consider extreme cases. So can anybody give me some extreme cases for k and m? So, but okay, so do you know that you'll be able to get m equals 1 if k equals 1? Did you say m or did you say n?
M.
Okay, so you don't know that you'll get m equals 1 if k equals 1. You could do k equals 1. So imagine k equals 1, and you have n tanks. If you have only one observation from 1 to 100, where do you think it would be? In the middle. If you had from 1 to 1,000, where do you think it would be? In the middle. So if you have one observation, what do you think the value of that would be in terms of capital N? On average, it would be 1/2 n. So you would want to double it. So look, when k equals 1, we basically double the largest value. That's reasonable. There's another extreme we could do. That's one observation. What's the other extreme in terms of observations? K equals, which is it?
I thought it was M, but I guess it's N.
I could just be playing with you. I've been known to do that. So m is going to be the largest serial number you observe. So you don't necessarily know what that's going to be until you start gathering your data. So you can't be sure. There's only one way you can know what that largest serial number is going to be. What's the one way you know for sure what that largest serial number is going to be? If k equals
N.
n.
If k equals n, then m will certainly be n.
Yes, if k equals n, you've observed everything. And if you've observed everything, then m has to equal n. I was at a Phi Beta Kappa national meeting. You have to receive a majority of votes to be elected senator. There have to be 2 people for each position. 9 people had to be elected. We had 18 candidates. We had a couple of people who got elected very quickly. And after a while, we had, I think, 10 candidates left for one remaining position. And nobody was close to 50%. And we were just going back and forth. And somebody said, why don't we just throw away whoever has the fewest votes? And says, no, you can't do that. This is just a sample. It may not be representative. And somebody said, this is not a sample. This is a complete survey of the population of voters. It's not a sample. Like, oh yeah, you're right. And so here, if we observe all n, then we know m has to be n. There's no way around it. As an aside, there was then a motion to throw away whoever had the fewest votes, but that required a supermajority because it was changing procedures in the middle of an election, and that failed. Then there was another attempt to change procedures in the middle of an election, and that failed. And then I raised my hand and said, Steve Miller, mathematician, Williams College, I am not making any proposal. I would just like to state for the record, if people don't want to vote for whomever had the fewest votes, thank you. And because that was not a motion, then in 2 more votes, we were finally able to elect the last person. So if we look at the case when k equals capital N, then you get capital N times 1 plus 1 over n. That's going to be n plus 1 minus 1 is capital N. So the formula works in that case as well. This is not a proof, but it does show that it matches the intuition we have that it should be increasing with m, decreasing with k. The extreme cases, it works. This is more important than almost anything else I've taught you this semester. This ability to look at a problem and get a sense of, is this reasonable? Can you look at extreme cases? Can you get a feel for the problem before you even start? You get a sense of what the answer should be. This is the skill that you are going to use. You are not going to use facts about the chi-squared random variable. If you ever need to, what will you do? You look it up. I needed a result from one of my papers. Rather than go to my computer and look up the paper, it was faster to just type it into Google, and I knew Google would pull it up faster than I could search the directory structure. The information is so readily available. What you need is asking the right questions and getting a feel of, is the answer reasonable? So we talked about, we did the sanity checks. Okay. So here is the key lemma, and this is a nice probability lemma. So let capital M, because we use capital letters for random variables, lowercase letters for the observations, be the random variable for the maximum number observed. Little m is what we see. There's, of course, zero probability that we see anything 0 or less. In fact, there's zero probability that we observe anything less than k. And there's zero probability that we observe anything larger than capital N. So for any k between, for any m between k and n, the probability that the largest observed serial number is little m is the following: m minus k, m choose k minus m minus 1 choose k divided by n choose k, or just m minus 1 choose k minus 1 divided by n choose k. So there's two ways to prove this. The first is, can somebody tell me what the denominator represents? What is the n choose k? Good, it's the number of ways we could observe k tanks. So the numerator must be the number of samples that have little m as the largest value. So the first one is m choose k is what's the number of ways I can choose k tanks from m. So that means m is going to be possibly the largest, but maybe I don't choose m. So I know with m choose k, I can only choose k tanks whose serial number is at most m. I then subtract off m minus 1 choose k. These are all the tanks whose largest observed serial number is at most m minus 1. And whatever's left over has to have largest serial number m. Using Pascal's identity, I can simplify that to m minus 1 choose k minus 1. I can also use this to give another proof of Pascal's identity. If I want the largest serial number to be m, I have to choose m. How many choices do I have left now? I've got to observe k tanks. I've chosen one. How many tanks are left to observe? K minus 1. And the largest I can observe is m minus 1. So that's where the m minus 1 choose k minus 1 comes from. If m is the largest, then I have to choose k minus 1 from m minus 1. Okay, so that the text over there is just what we basically just said out loud. Okay, so we should all by now know the definition of expected value. It's just the value times the probability the random variable takes on that value. And then if we substitute for the probability of observing little m as the largest, we have this sum to consider. Any thoughts about how we should evaluate this sum, how we should try to get a feel for it? What could we do? It's okay if it's wrong. What are your thoughts about how we could try to do this? So we have a sum over m. The denominator doesn't depend on n. And the numerator is m minus 1 choose k minus 1. What could we do to the numerator? What do you know about m minus 1 choose k minus 1? How would you compute 8 choose 3? What's 8 choose 3? 8 factorial over 5 factorial, 3 factorial. We could try to expand this out and then try to do some algebra. So if we expand it out, it's going to be m minus 1 factorial over k minus 1 factorial, m minus k factorial. I can expand out the n choose k if I want, and I can do some cancellation combining. So the m times m minus 1 factorial gives me an m factorial. And I just try to play some games. Oh, look, it almost looks like m choose k. I've got an m factorial and an m minus k factorial, but I have a k minus 1 factorial. Well, I can make the k minus 1 factorial a k factorial by multiplying by k over k. And now I've got, if I factor things out a little bit, I have something that doesn't depend on m, and then I have a sum of m choose k. Well, now it's probably clear why I spent some time earlier in the lecture talking about the hockey stick identity. This is now exactly what the hockey stick identity can give us. It can give us a closed form expression for this sum. This is where the miracle occurs, that we happen to have a sum that has a nice closed form expression, and we're going to get an answer that depends cleanly on capital, on k and lowercase m. In general, we are not going to have formulas like this. This is where the miracle occurs. And so we get n plus 1 choose k plus 1. Okay. So we can do a little bit of algebraic simplifications. And if we continue the simplifications, at the end of the day, after you do the algebra, you get k times n plus 1 over k plus 1. And that's the expected value of m, which we believe is little m. So now we can solve for n. If we have little m equals this, then just solve for capital N. And you get capital N equals the expected value of m times 1 plus 1 over k minus 1. And then just putting in the value for the expected value, little m, we get the claimed formula. So it wasn't too bad to get this. The algebra wasn't that bad. Yes?
So, it's like fair, when is it fair game to just sort of switch? Because we're kind of going from expected value of m to expected value of n, right? So like this.
So we have a formula for n in terms of the expected value for m.
Yeah.
So then we just put in our best guess for the expected value.
Yep.
And that will become our best guess for n hat. And then you can develop an entire theory that will talk about how will the errors propagate,
Sure.
what will the variances be.
Yep.
But if I had to guess for n, this is a very justifiable guess.
Certainly, yeah. Is it wrong to say that n hat is like the expected value of n, or is that?
Well, the thing is, we observe one value of m.
Yeah.
And so we only get one
Given that observation.
Given that observation.
Yeah.
It's our best guess for the expected value of m.
Okay. Yeah.
And so the question then becomes, what if we had multiple observations? And so what if we do this a lot of times? And we could actually simulate this. So if we're not sure about what the formula is, and we're going to get to this later today, what if we did this experiment 1,000 times? And for each time we get an m, and then we average the m, and then use that. So we could do this on the simulation side, and then say, hey, this is suggesting the following formula. So if we think that n is a function of the expected value of m, maybe a linear function of the expected value of m, times maybe a factor that has some strange k dependence, and we'll get to that later today, where we will exactly want to do that. Okay, I'm not going to spend too much time talking about how do you extend this to an unknown lower bound. I just want to do a small amount. How do you think n hat should depend on m1, m2, which is going to be the smallest and largest serial numbers, and the number of tanks observed? So I'm going to let S be the spread. It's going to be m2 minus m1. So what should happen as the spread goes up and increases? What should happen as the number of tanks goes up? So if you have the same spread but for more tanks observed, what should happen to your guess for n hat? It should go down. What's the smallest n hat could be? Well, before we said the smallest it could be was m. What should the smallest n hat should be now?
m2 minus m1. Oh.
Almost. Let's say your smallest is 3 and your largest is 5.
So m2 minus m1 plus 1.
Plus 1, right? You have to remember to add the 1 because for the spread, if I have 3 and 5, that's actually 3 integers, not 2 integers. So you might guess that it's s plus 1 is the lower bound, and then I have some formula. And what would be your guess in terms of a functional form of s and k? So before we had it was m over k. What do you think it is now? Or just s over k? It's not. It's k minus 1. Can anybody tell me why it's k minus 1 and not k? Can you calculate an expected value with one observation? So if I tell you on the final, somebody in the class got a 93, what would you estimate the class did on the final? That's all the data you get. What would you estimate? 93, right? There's nothing else you could do. What would you estimate for the variance in the class if you only have the observation of 93? You can't say anything about the variance with one observation. If I only have one observation, can I measure a spread? No, there's no way I can measure a spread with one observation. So the formula should break down if I try to do this with k equals 1. And that's why we have the k minus 1 down there. Some of you might have seen stuff like this if you've taken the stats class in the sample standard deviation in terms of dividing by n minus 1 and not dividing by n. So if you've seen that in statistics, it's very similar reasoning going on over here. And so the answer is just s times 1 plus 2 over k minus 1 plus 1. And again, you always want to see, is the answer reasonable? It looks very similar to what we had before. We have a k minus 1, not a k. And we now have a factor of 2. Does the factor of 2 make sense? Can you give me a story? What would be the story of why we have a 2? So in the original problem, we knew we started at 1, and then we had an unknown capital N that we walked up to. Now we don't know where we start. How many directions do we have to go? We have 2 directions, going up and going down. So it kind of makes sense that it should be doubled. So the proof is very similar. We need to calculate a formula for the probability that the spread equals S. You can prove it very similarly and get a nice relationship like this. And then you have to do some algebra. There's a lot of multiplying by 1 or adding zeros to make everything work. I have gone through and I have put those details in the appendix at the end. Nobody wants to see this level of algebra in class, but the details are there. And that was done with Williams students and published a couple of years ago. So here from Wikipedia is a couple of months in World War II. You have the estimate from statistics, 169, 244, 327. You have the intelligence estimates, 1,000, 1550, 1550. So which do you think is closer, the stats or the intelligence? Stats, by a lot or a little? A lot. It's not even close, 122, 271, 342. It's amazing how well it did. Now, it's not enough to be right. You have to be able to convince people to do your recommendations. Yes?
Oh, I guess I was wondering if the incentives, like, if I was a nose officer, I would be like, first more if I guess like lower than if I heard higher.
Right, and so there's a lot of things where you want to make sure you make an error in a certain direction. For example, bridges, elevators, right? Do you think the capacity of the elevator is exactly what it says? No. You know, they're not going to have it that close. They're going to have some kind of safety margin. How much of a safety margin? It's expensive to put in these safety margins, but it's very expensive when they fail. And so certain types of errors you want to protect yourself from. But if you protect yourself too much, then you are misallocating resources. And so it's a really interesting question as to how do you make peace with these various things. Okay, so what I want to do now is I want to talk a little bit about regression. I know we just covered this stuff on Tuesday. No, today's Tuesday, so on Thursday. But it's a really important concept, and I want to just quickly go through it again. So when we were trying to find the best fit line, it's best fit with respect to what metric. Depending on what metric you choose, you're going to get different things as best fit. We talked about there were 3 choices, just looking at the difference between predicted and observed, the absolute value, or the square. And we chose the square because now calculus and linear algebra are available. The square function is differentiable, the absolute value function is not. And having signed errors is absurd because if you have your data, say bottom left and upper right, the line connecting them is just as good as the line going from the top left to the bottom right. It's absurd. You never want to deal with signed errors when you're doing your analysis. But if you put an absolute value, calculus is not available. So we use sum of squares, so we can use calculus. And then all we have to do is we find the partial derivatives, we set them equal to 0, and then we have a system of 2 equations and 2 unknowns, and the unknowns a and b. We know that there is going to be a minimum for finite values of a and b, because as a and b go off to infinity, then the error is just getting incredibly large. So we're lucky. We know that if we stay in a compact set, a closed bounded set near the origin for a and b, we will have a minimum value. I don't have to go to advanced results from calculus and talk about the Hessian, the matrix of second partial derivatives, and whether or not this is a minimum or maximum. We know it's got to be a minimum when we do this. Okay, and again, the reason this works is if your first derivative is positive, then you're increasing if you go in that direction, and you're decreasing going backwards. So the only possible candidates for maxima and minima is when the derivatives are zero. So we take the derivatives, we set them equal to zero, and then we just do some algebra. And so when we set them equal to zero, we can pull out the a and the b. We have two equations and two unknowns. We can write this in matrix form, we can solve, and we get our best estimates for a and b is the inverse of this matrix. And we talked about how the determinant of this matrix is actually the variance of the SIs, of the XIs. Or maybe it's up to a factor of n. But it's basically a nice multiple, a non-zero multiple of the variance. So as long as the XIs are changing, then the determinant is non-zero and you can invert. The only way the X's would not be changing is if, no offense, and we've talked about this before, you're a moron. Yeah, there's no nice way to phrase it. Sometimes you just have to be brutally honest and say you screwed up. You're trying to determine how y depends on x, and you kept x fixed. You're not going to determine how y depends on x if you don't change x. I want to see how the slope of the inclined plane affects how long it takes the ball to roll down. And I'm always going to do it at 30 degrees. Okay, great. You'll figure out what's going on maybe at 30 degrees, but you're not going to figure out how it changes with the angle. So we really don't have to worry about this matrix not being invertible. We talked about how many nonlinear relations become linear when we take logarithms. This is another of the big themes of this class. Whenever you have some data, consider a transformation. And maybe in a different variable system, it's going to look better. And so if I apply logarithms, a lot of things become linear. We talked about Kepler's third law, which is the period squared is proportional to the cube of the semi-major axis. You can, of course, just divide both sides by, as I take the square root of both sides, you might as well adjust it so that the period is to the first power. You don't really have two free exponents. And so can we discover this through statistics? Well, if we look at the data for the semi-major axes of the planets, and we look at the orbital periods, we have chosen units so that Earth has essentially units for one for distance and unit one for years, so that our constant b should be approximately 1, and we get a beautiful, beautiful line. So the exponent was supposed to be 1.50, we get 1.49986. That's not bad. And this is assuming that the only force of gravity in the solar system is the sun, and whatever planet you're looking at. Is that a reasonable assumption? No. Now, Mercury is probably not doing that much to Jupiter, but Jupiter might be doing something to the planets near it. And in fact, this is how Uranus was discovered, is that the orbits of, Neptune. The orbit of Uranus was doing well for decades, but then it was a little bit off. And so it was predicted that maybe there is a planet beyond the orbit of Uranus, which occasionally gets close enough to it that it impacts its orbit. And because the planet is so far away, it's not going to screw up the rest of the solar system. And they discovered the planet Neptune by analyzing orbital deviations in Uranus. It was masterful. Okay, we've talked about using statistics to describe the real world. We've talked in the past, I just love showing these slides of SMUT, where one of the fraternities at MIT wanted to see how many times it would take for them to put their pledge from one end of the bridge to another. It was, I think, 364.1 SMUTs plus or minus an ear. Love that accuracy. We did the birthday problem at the start of the year, I think, yes. How many people do you need in a room before you have a 50% chance, assuming that all the birthdays are random? If I was doing this to a large team on campus, that's not necessarily a reasonable assumption. And there's a great passage in the book from Malcolm Gladwell where you want to be essentially the oldest kid to just miss making a league, because then you'll be, when you're very young, you'll be on average a little bit larger, a little bit stronger, so you'll look better, so you get more playing time, and it propagates all the way up. And so the distribution of birthdays is a little bit off in sports. But if we assume that things are uniformly distributed, we talked in class that it's roughly proportional to the square root of the number of days in the year. It was actually d to the 1/2 times the square root of the log of 4. We could try to do this with simulations and try to see, could we predict this? And so if we take logarithms, so we want the probability, some constant d to the a, so the log of p is a log d plus b. When we did this, we got a was about 0.506, which is pretty close to a half. I did it with, I think twice, 10,000 simulations with d chosen from 10,000 to 100,000. So, again, it's wonderful to see how well data analysis can do in terms of predicting what the answer is. We proved the square root of d by doing Taylor series expansions, taking logarithms, doing a lot of analysis. Then we had sums, and we used formulas for sums of powers. And then we had like a quadratic formula, and we approximated things. And when everything settled, we got d to the 1/2 square root of log 4. By just simulating, we're able to see that it looks like it's the square root of d. And again, this is the power of being able to write some simple code and gather data. You need to be able to do this in the 21st century. So here's trying to do some things for the German tank problem, looking at n minus m as a function of m over k. That almost looks like a tank trajectory being launched off like this. It's really bad. I don't want to go into now why this is really bad. I'll talk about other things that are bad, but if people are interested, just let me know. So if we try to do a two-dimensional plot, it actually does a pretty good job. But again, I don't really want to go too much into the advanced statistics here. Just letting you know, if you continue in statistics or econometrics, you will have stuff like this where you'll be estimating things as functions of several variables and trying to get good prediction, and it is possible to do that. All right, so I want to talk about the implementation issues and how, if you did not have a ease of doing combinatorial calculations, if multiplying by 1 and adding 0 is not something that's natural to you, how could you sniff out that it's m times 1 plus 1 over k? We're not going to get the minus 1, no offense. That's beyond us, but it doesn't really matter, okay? If we're often calculating one tank out of 100 or 1,000, not a big deal. I want to get the k dependence. I want to get the m dependence. I'm going to show you how to do that today. So here is trying to figure out our formula is n is 1 plus 1 over km minus 1. And I'm going to plot n versus the maximum observed tank when k equals 1. The theory says n should be 2m minus 1. The best fit value, looking at the data in this region, is n is 0.784m plus 2875. Is there any way that that best fit formula can work for all values of m? Why not? So I saw you shaking your head. Why can't this work for all values of m?
Well, like we talked about earlier, if n equals 1, then why are we adding 2,875?
So in that case, we'd probably get little m equals 1, and so it would be off by a little bit. It would be off by almost 3,000. It's a little concerning, but maybe you have to pay a price. Maybe you overestimate for some small values, and then you make it up in larger ones. But you can look at this and you can tell me.
Well, I mean, if we have a very large maximum tank number observed,
Okay, so
at a certain point, we're going to the difference, like because we're multiplying it by less than 1.
Good.
Yeah. It's going to go down.
Good.
Yeah.
So we're multiplying it by something that's less than 1. So eventually, the 0.784m plus 2875 is going to be less than m. So you're going to be the ridiculous case where the predicted number of tanks is going to be less than the largest serial number you observe. And the larger m is, the worse it's going to be. So this is a formula that works fine in the range of gathering tanks for maybe 10,000, maybe 1,000 to 10,000. In that range, it does a fine job, but it can't do a good job everywhere. I know that there's something has to be wrong. And so it should be a little concerning to you that we have such a bad result. But I did something illegal. What did I do? Well, so I've restricted that, but that's not really the bad thing I did. So what am I doing here? I'm looking at the number of tanks as a function of the maximum observed. And what I'm doing for my simulation is I'm choosing n, and then I'm sampling one tank from that n, and I'm recording m. Which is the dependent variable? N or m? Which, right, the way I've put it, I've put m on the x-axis, m should really be on the y-axis. I've actually flipped things. It's n that I'm choosing. I'm really predicting m as a function of n. And so it's a really subtle mistake, but I did something I shouldn't have done. When I did the method of least squares, y was a function of x. You give me, and so I flipped the relationship. If I take k equals 2, it's a little bit better, but you see the constant in front of m, 0.964, is still less than 1, much less than the 1.5. So I know this has to be bad. If I take k equals 5, I get 1.037. This is almost like breaking the sound barrier. I've at least reached the point where it's not complete bullshit, right? I have something that's now growing with m. I'm inflating by something, okay. And you can see the data is a little bit more concentrated, but it's still a little bit off. But it's not off by a terrible amount now. It's 1.037 versus 1.2. And of course, as k gets larger and larger and larger, the constant is converging to 1. So it's not surprising that it's getting better and better and better. If we flip things, if we write m as a function of n, then we get m is k plus 1 over kn plus a small constant depending on k. And now when I try to do this, if k equals 1, it should be m is about 1/2 capital N. And when I do the experiment, I get 0.496 capital N. That's pretty good. And if you look at that, the line is pretty nicely centered. And so if I put the variables in the correct spots on the plot, I'm actually doing a decent job. Okay? So this is the power. If I didn't know this relationship, I would say when k equals 1, it looks like the factor is about 1/2. When k equals 2, I get 0.668, and the correct answer is 2/3, about 0.667. Again, pretty good. When k equals 5, 0.828 versus 0.883, not bad. Here's another trick you can do, which was related to the earlier question about expected value. What if I don't want to do these tricks? What if I really want to write n as a function of m? Well, let me do 100 runs for each n and average those and put those values in for m. And if I do that, I actually do a very good job. And now that tightens things up. And the theory line is 1.5 m. I'm getting 1.496 m. And so doing a little averaging like that does a great job. And in an advanced stats class, you would start talking about these various tools and techniques. How can we look at the data the right way and make good predictions? Okay. So what I want to end today on is the sad situation where we can't do advanced mathematics. It's a terrible world, but we can't do advanced mathematics anymore. But we are able to gather data. And so can we sniff out the functional relationship with the data? So the correct answer is n is a multiple of m minus 1. What is that multiple? 1 plus 1 over k. And so let's say I conjecture that capital N should be a times m plus b, where a and b are functions of k. Okay? I could fight a tremendous number of battles and after each battle collect the serial numbers, or I could just simulate this in the lab. It's not that hard to simulate. With computers nowadays, it's no problem. If you don't have a computer, take a large bucket, put in pieces of paper, and pull them out. Okay? And so what I'm going to do is for each choice of k, I'm going to do the experiment maybe 1,000 times, 10,000 times, 1,000,000 times, and find what's the best fit line for each choice of k. And I'm going to record that here. And so the x-axis is the number of observations. It's the value of k. The y-axis is the best fit value of a, when I do the method of least squares. So as k increases, the multiple of m seems to decrease, and it seems to be decreasing towards 1. Does that make sense? Yeah, the larger k is, the more I've seen And the closer my largest observed is going to be just to the total number of tanks. So this seems reasonable. Can anybody look at this and immediately see exactly the functional form is 1 + 1 over k? No. What could we do to try to see this data in a better light? I'm sorry? Good. How should we plot it? This is a Miller class by the end of the semester. What should you do? Take logarithms, right? When in doubt, take logarithms. Now, I can plot the log of a versus the log of k. But rather than plotting the log of a, there's something better to plot than the log of a. Do we agree that in the limit a goes to 1? And do we agree that it has to be at least m plus something? Because the total number of tanks can't be smaller than m. So really, I know a is 1 plus something. So rather than plotting the log of a, I should plot the log of so instead of log of a, what should I subtract from a?
1.
1. So let's plot the log of a minus 1. And if I plot the log of a minus 1 versus the log of k, does that look like a straight line? We are now discovering this relationship entirely based on data analysis. And when you look at this, the best fit line, and again, you can't make this up, is 0.999 log of k minus 0.007. There's a very nice twist. And so looking at this, we would conjecture that n is equal to 1 + 1 over k times m minus some constant that depends on k. That constant is not so important. What really matters is how do we scale things as a function of the number of observations. And we are able to sniff out the k dependence just by simulating. And so when we're doing the algebra, if we're having trouble, we could now figure out what that is. Just putting things up. I know we've done this before. Who remembers where Smoot ended up? Chairman of the American National Standards Institute, president of the International Organization for Standardization. And again, I know I've said this before, but the more times you hear things, the more likely it is to stick with you. There's a tremendous number of smart people. The phrase is, you're 1 in a million, which means there's 1,000 like you in China or India. You need to distinguish yourself. You need to find a way to shine and to have people remember you. Williams has the oldest what? Alumni society. That is a wonderful advantage you have being at a school like this. Take advantage of that. Make sure you get to know at least one professor well a semester. We frequently have opportunities, and if you let us know what you're looking for, what you want to do, when something arises, we know who to send it to. And if it's not right for you, it might be right for one of your friends, and it can then go through your network. So that's really one of the huge value added at being at a school like this. And again, I'm always happy to meet with people. My schedule is often in flux, but shoot me an email, even if the semester is over, always happy to chat. Everything is an opportunity. The older you are, the more established you are, the less important the opportunity is. I'm about to go to a birthday conference where I got on someone's radar because we happened to go to 3 conferences together within a month, and he heard me talk about 3 different projects I did with 3 different student groups. And that got me on his radar screen. And so when you're young, every time you give a presentation, this is an opportunity for you to shine. Now, you want to get comfortable speaking up. I think a lot of you know the answers to the questions I'm asking in class, and I'm just afraid to answer, oh my God, this is too, I want you to just get used to speaking. The more you speak, the more likely you are to speak later in life when it really matters. And you can then be noticed by people. I don't want you to just be the person coding in the basement. I want people to be aware of what you're doing and the value that you're adding. Smoot could have easily put up a struggle and fought when this was being done. Or you can just roll with it, literally. And it turned out to be an interesting story for him. Part of my success in mathematics is my thesis advisor had 2 Steve Millers born same year, same city. You're like, what, is he lapping the community? He's on his 2nd Steve Miller? And it just helped a lot of people get to know me because he, even though he's a few months younger than I am, he's smarter than I am. He graduated my first year in grad school because he skipped many grades. And he made a name for me in the mathematics community. So take advantage. You don't know where these are going to lead. You don't know the connections. So there's a bunch of papers I've done. This actually should be added because I've done more papers with students since then. I just very briefly, just so that the slides are on the YouTube video and anybody can then pause. If you wanted to do the more involved calculations, you just write down all the different quantities if we're going to be looking at spreads. And then you just write down, using like the hockey stick identity and stuff like this. And you just start calculating what is the expected value of the spread. And you see eventually after some algebra, the expected value of spread is the difference of two quantities, T1 and T2, which means we have to work with T1 and T2. So we first work with T1, we do some algebra, and then, shocker, after working with T1, we work with T2, do some more algebra. And unfortunately, T2 is a little bit more complicated, and we have T21, T22. This is hopefully good notation. T21, T22, these should be things coming from T2. You want your notation to be great so people can quickly look down and see what you're doing. I don't really want you to be looking at the actual algebra. I just want you to be looking at the notation as to how I'm setting things up. All right, so now we try to calculate what T22 is, then we calculate T21, and we end up getting some formulas for it. And then we just substitute everything back, and then we do some cleanup. And again, if you have an idea of what the formula should be, that helps you figure out how to clean things up. I'm expecting something like spread over k-1 when the dust settles, or I can multiply back and see how things should be. And then when everything settles, we get something like this, where now we're going to actually get a factor of 2 over k-1, and that factor of 2 is quite reasonable. All right, so this is a good place to stop for this. Again, what I hope you got from this today is a review of a lot of the material we've done, and to see that this actually can be used in the real world. As an aside, how many of you have ever seen a tip jar? What goes in a tip jar? Cash, right? This is almost like asking who's buried in Grant's tomb, right? Tips. Who puts money in the tip jar?
The employee. The customer puts it in. Also, the employee first puts it in.
Good. So it's not just the customers who put money in the tip jar. The employee often puts money in the tip jar. Why? So customers think of doing it because they say, oh, wow, people are putting things in. And you might even put in some $5 bills, some $10 bills. Wow, people are, I guess, generous at the store, right? Can you trust what you see in the tip jar as coming just from customers? That's very similar to the German tank problem, where you don't necessarily start at 0. You don't necessarily start at 1. If you are a business and you are negotiating your first contract, tell the customer, we're really looking forward to finally getting a client. You're going to be number 0000001. So sometimes you might want to encode things so people do not necessarily know what volume are you doing, how big are you. So again, especially in the 21st century, there's so much that can be done with the data that you put out there. You might want to really think along the lines of the German tank problem. What can people run on the data you're publicly presenting? Are you giving your competition some information you don't want them to know about just how big you are, how productive you are? And so if you start encoding these things, they may not be able to do those calculations. So again, a lot of the stuff that we're doing has tremendous real-world applications. There's a lot of stuff that you can do either on the data analysis stat side or on the theoretical math side. All right, and so this is a good place to stop. So we will stop.